geometric isomerism. Okay, geometric isomerism. This is shown by two types of compounds. This is shown by two types of compounds. Number one, double bonded compounds. And number two, ring compounds. Now, in the case of double bonded compounds, you have a double bond, you have identical groups on one side, A, B, and H and H. Or you can put carboxylic acid. Why do you want to generalize it? COOH and the double bonded H, COOH and COOH on the other side. So this type of compound in which you have different groups directed in different direction across a double bond. Okay, and remember this molecule will not show optical geometric isomerism. Suppose the carboxylic acid are on the same carbon. I mean, two groups, identical groups are on the same carbon, there will be no geometric isomerism. Okay, here also it is the same thing. So there is the two groups on one single carbon should be different, and only you can put them in the opposite direction. Okay, so that is geometric isomerism. Basically, you can have any four groups here. Now, in the case of ring compounds, see here, this is cyclohexane molecule with methyl group here and here. This is a trans compound. And the same methyl group you can put on the same side. Sorry. Same methyl group you can put on the same side of the ring. So this is cis compound. Okay. So this is geometric isomerism in the case of ring compounds. Now, why geometric isomerism? Because rotation around a double bond is not allowed. You cannot rotate a double bond. Okay. On its axis, you cannot rotate it because the double bond is having a lobe on the other side, this side as well as this side. So you cannot rotate it along the double bond. And therefore, and that if you want to convert this into this, you have to break the bond. The pi bond has to be broken and then you can change it. Now, you can write any different example for this. And I will distinguish between cis and trans isomers. And generally, trans is more stable. Trans isomers are more stable. Okay, that is because of certain physical properties. Because the crystal structure is more compact. Okay, crystal structures are more compact, and they have different properties. In fact, all the properties are different. Suppose you have this molecule. If you have this molecule in which the carboxylic acid is on the same side, this is called maleic acid. And this is called fumaric acid. Okay, malic acid, if we are heating malic acid, very easily it will remove a molecule of water. Very easily. Okay, at around what is the temperature? About 40-50 degree Celsius. 50 degrees Celsius, it will remove a molecule of water and will form malic anhydride. See here. That means one H from here and one OH from here. It got combined and forms malic anhydride. Okay. Now this is not easy. In this case, it is not very easy. You have to heat this up to 125. This molecule has to be heated. Is it 125? That is 100, yeah. Approximately 125 degrees Celsius. You have to heat it. Then only then it will form this compound, the same compound here. Because you know it is not possible to form a bond from here to here. It is too far away. It is not possible to form a bond from here to here. So what must be happening? When you increase the temperature, the double bond is getting broken. Okay? So what happens is, when you increase the temperature, the double bond is getting broken and the molecule rotates and it forms this compound. And then a molecule of water is eliminated instantly to form the malic anhydride. So if you heat malic acid or fumaric acid, you will get only malic anhydride. But in the case of fumaric acid, you require high temperature to form. That is because the carboxylic acid groups are opposite side. They have to come closer to form the cyclic ring. To become closer, the double bond has to be broken. That is, and for that purpose, high temperature is required. Okay, so that is basically. Now, how will you distinguish between the cis and trans isomers? This is one method. Okay. Second method is in terms of melting point. You check the melting point. Cis isomers have lower melting point. Cis, lower melting point. Trans, higher melting point. Trans, high melting point. So you can easily recognize them based on this. Another method is based on dipole moment. Dipole moment. Based on dipole moment. You can see here, there will be a positive dipole moment for the cis compound. See what is dipole moment? See here, polarity of each bond. See, this bond is having this dipole towards this direction. The dipole moment of this bond, this is CO bond, will be towards this direction. And this also will be in this direction. So what is the net dipole moment will be in this direction. So this side is positive, this side is negative. But in the case of trans compound, COOH and COOH. This dipole moment in this direction, but here the dipole moment is exactly in the opposite direction. And here also H in this direction. And here in the opposite direction. So the net dipole moment is 0. The net dipole moment is 0. Here the net dipole moment is more than 0. It is positive. Okay. So you can apply this on any of the cis and trans compound. So that is what is geometric isomerism and how you will distinguish between geometric isomers. Now let us come to optical isomerism. What is optical isomerism? Ability of a compound. Ability of a compound. Ability of a compound to rotate plane of a plane polarized light to either left or right. To left or right. This is what is called optical isomerism. Now let us see what is this stuff. Okay, ordinary light. If you take a bulb, ordinary light has all wavelengths, all possible wavelengths. Okay, see, visible light is within the range of 300 to 700 nanometers. I'll say 400. This is visible light, 400 to 700 nanometers, 700 to 750. Okay, so if you take that light, then if you take ordinary bulb or something, it will give out all these wavelengths. And that also, these waves will be moving in different planes. Some of the wave will be moving. Some waves will be moving in this direction, see here, in this plane. Some other wave will be moving in a perpendicular plane. Like this. Some of them will be moving in this way. In different plane. Okay. See that. All these in different plane. So all possible wavelength in all possible direction, in all possible plane. So that is what is called ordinary light. That is what is ordinary light. But in the case of monochromatic light, you are choosing the wavelength. Okay, it will have a constant wavelength. You are taking out only one wavelength, only those rays which are having a constant wavelength, but moving in all possible direction, all possible plane. See, wavelength is correct, wavelength is same, okay, but some of them will be moving in this direction, some of them will be moving in this plane. In different planes they move. So that is what is called monochromatic light. This is obtained by passing ordinary light through a simple prism. If you pass ordinary light into prism, what happens is it forms VIBGYOR. Okay, violet and red, VIBGYOR. So that means you have split this into different wavelength. Now you can choose which light you want by putting a small opening on the screen. So only this light will pass through it. Or this light, this part as well as this part is concealed. So you have kept a small opening in the path of the light after dispersing through the prism. So you can choose the wavelength. Okay, so that is monochromatic light. Now we have to convert the monochromatic light into plane polarized light. I'll clear the board first. We have to convert a monochromatic light into a plane polarized light. This is done by diffraction grating or Niccol prism. This is done by passing the light through a Niccol prism. It's actually a crystalline form of calcium carbonate. Niccol prism is a crystalline form of calcium carbonate. Okay, so now all the waves will be moving only in one plane. Suppose you have planes moving, that is waves moving in different planes. What happens is when you pass it through a slit, a Niccol prism, suppose this is Niccol prism, then only this wave will come out. The wave which is moving in this direction will be caught here, will get stuck. It will not pass through this. Okay, so this is what is called a plane polarized light. A plane polarized light. Now the plane polarized light, if you pass through an optical solution, if you pass the plane polarized light through an optically active compound, solution of an optically active compound, the plane of polarization will change. Okay, meaning suppose this light is passed through a small tube containing optically active compound. This contains a solution. What happens is the light wave will enter in this plane. Now it will slowly start changing the plane. See here. The whole ray is getting rotated. The one which is coming in this plane, in the plane of the board, will get rotated and become nearly perpendicular to this plane, nearly perpendicular. Okay. So this is what is called optical activity. And how do you measure the optical activity? Optical activity is measured by polarimeter. What are the different parts of a polarimeter? Polarimeter contains a light source of constant wavelength. A light source of constant wavelength. What is the meaning of constant wavelength? A source of light which produces monochromatic light. An example is sodium vapor lamp. Sodium vapor lamp. Now, sodium vapor lamp, it produces a light wave having 589 nanometers of wavelength. So the wavelength is fixed. So that has become a monochromatic light. Now, you have the monochromatic light. Now you have to polarize it. You pass this light through a Nicoll prism. Nicoll prism. After passing through Nicoll prism, you pass it through a, this is a Nicoll prism. It is passed through it. Now the light will come inside. Now what do? You take, this is called a polarimeter tube. It's having a definite length and dimensions. Okay. Now what do? You fill the tube with water. Fill the tube with water. And observe from here. And see whether you can see the light wave coming from here. By keeping a slit, analyzer slit. This is an analyzer. So when this slit and the Nicoll prism are aligned, they are aligned in the same line, then you can see the light from here falling on your eye. Remember, this is done on a microscope. Microscope is a type of instrument. So you just observe it through this. An eyepiece will be there. So you observe from here and see that you get the view of the light which is coming from here. Okay, you can see the light. Now you take this tube out and fill with optically active solution. Fill with a compound containing optically active, a solution containing optically active compound. Now, observe from here, you will not see this light coming out. You will see darkness. You will see darkness. What do? Rotate the slit, either clockwise or anti-clockwise. Rotate this slit like this. See here. Rotate this slit. And keep rotating and see at what position you can see the light. You see the light. at what position of this slit you can see the light. Find out that position, stop rotation, where the moment you see the light. Now the instrument will be having some measurement device. Measure this angle. That is called observed rotation. Measure that angle. That is called how much you have rotated. That is called observed rotation. Okay. So you have found the optical activity. Now, optical activity is proportional to different factors. It depends on different factors. Optical rotation depends on different factors. Depends on, or we can say proportional to. Number one, concentration of solution. Number two, solvent used. Solvent used. Number three, temperature of measurement. Number four, wavelength of measurement. And there is number five, path length of the solution. Path length of the solution. Go on. One second. Oh, what happened? One second. Something went wrong here. So path length of solution. Now let us look at each one of them. See here. It is a concentration of solution inside. If you increase the concentration, optical rotation will increase. That is one. Solvent. In one solvent, you will have one optical rotation. In another solvent, you will have another optical rotation. So, whenever you make a study of optical rotation, you have to use only one solvent and report the name of the solvent you have used. If we change the solvent, the optical rotation will change. Okay. So normally we use only one solvent for a compound and we report that. So that means you will not change this. This will be a constant. The temperature, always we measure this at room temperature, which is taken approximately 25 degrees Celsius. So that also we have made constant. Now wavelength also affects. So what we do is we take only one wavelength, that is 5,8 wavelength having 589 nanometers. And this wavelength is corresponding to that of sodium vapor lamp. Sodium vapor lamp. Okay. So that also is constant. The last one is called path length. What is meant by path length? This distance is called path length. The distance from one end to the other of the polarimeter tube. That is what is called a path length. So if you want, you can have different cells, different tubes. Okay, so that also. So in short, what we can say is optical rotation. Optical rotation is proportional to optical rotation. Notation itself is alpha. Is proportional to this sign is for proportionality. The concentration of the solution C into path length of the solution L. All others are constant, right? So alpha is equal to C into L. Alpha is proportional to C into L. And now we will introduce the proportionality constant. Alpha is equal to a constant into that constant we will put in square bracket. That constant alpha, okay, into C into L. Therefore, the constant alpha, which we call as specific rotation, equals, what you have to do is you take this to the other side. Alpha, that is observed rotation, divided by concentration of solution into path length. So this is what is known as specific rotation of a compound. It is the optical activity of a solution containing 1 gram per 1 gram per 100 ml of optically active compound when passed through a polarimeter tube having 1 decimeter path length. 1 decimeter path length. This L is expressed in decimeters. L is expressed in decimeters. Okay. Oh, and concentration is gram per ml. Sorry. Concentration is expressed in gram per ml. So specific rotation is the observed rotation when plane polarized light is passed through 1 decimeter of the solution. Remember, path length is always expressed in decimeters, dm, 10 centimeter. Okay. So 1 decimeter of the solution of a substance having a concentration of 1 gram per ml. Having a concentration of 1 gram per ml. So if you take aqueous sucrose solution, sugar solution, you will see that the specific rotation alpha star is equal to, when you do the calculation, you can see specific rotation is equal to plus 66.5. Plus 66.5 degrees in water. So it mentioned the solvent also. Okay. So this is the specific rotation. That means, and when there is plus sign, that means this rotation is clockwise. This rotation is clockwise. So this stands for, and when the positive, when it is positive, it is called dextro-rotatory. Dextro-rotatory. Clear? So this is basically what is polarimeter and polarimetry. So next time we will discuss what is the cause of optical activity and why is optical activity definition of this stuff. Okay? Okay, we'll stop here. We'll continue on Monday. Thank you. എല്ലാവരും കുറച്ച് നേരത്തെ വരിക, എന്നാലേ നിങ്ങൾക്ക് അതിൻ്റെ അഡ്വാൻറ്റേജ് ഉണ്ടാവുള്ളൂ. കുറച്ച് നേരത്തെ എത്തുക. കുട്ടികളുണ്ട്, പക്ഷെ ഉള്ളവർ കുറച്ച് നേരത്തെ വന്നാലേ കാര്യം. താങ്ക് യു.